We are going to see how we can sketch a rough version of a phase portrait. Often we would just prefer to have a computer do this for us, but there's something illustrative in doing it ourselves and trying to understand what these phase lines and trajectories mean. This is a linear system of differential equations. We found the eigenvectors and eigenvalues in a previous video, and this is the general solution based on those eigenvalues and the eigenvectors. So we have the general solution to this one. What we want is a picture of the phase portrait. So let's get some axes for our phase portrait. And now step one is going to be sketch the eigenlines. We're going to put this in quotes because it's not a real word and it's not something you're going to find in a textbook, but it just makes sense to call these things eigenlines. What are the eigenlines? It's just a representation of the eigenvector. So 1, 2, and then turn that into a line through the origin. So that's eigenline number 1. Eigenline number 2 is 1, -2. So again, just sketch it and connect it through the origin. So these are the eigenlines. This one is for 1, -2. This one is for 1, 2. That's step 1 of this process. Step 2 is we're going to add arrows to the eigenlines. So how do we add arrows to the eigenlines? With the phase portrait, we have X and Y axes, and we could think of an initial condition of being anywhere in here, right? Placing us X is 0, Y is 0 could be here, here, here. If X is 0, Y is 0 places us on one of the eigenlines, that corresponds to having only one of these two terms in our solution. For example, if C1 equals 0. If C1 equals 0, then we don't have this part of our solution. We only have this part of our solution. So if we choose initial conditions such that C1 is 0 and we only have this part of our solution, right? The solution looks like C2 e to the minus t minus 2 e to the minus t. That puts us along this eigenline right here, right? We've zeroed out the 1, 2 eigenline. This puts us on the other eigenline, and looking at the solution, if I'm at some point on this other eigenline, the solution is decaying. Both the x and y components are decaying, e to the minus t, e to the minus t. Those are decaying, so the solution is going to go towards x equals 0 and y equals 0. It's going to go towards the origin. No matter where I am on that eigenline, I'm going towards the origin. And so I put arrows on it in this way, right? Now, the other eigenline, if it was the opposite, if C2 were 0 and C1 were non-zero, we would be on the other eigenline, and our solution would involve e to the 3t, which is exponentially growing. So both x of t would be growing and y of t would be growing. So we would be getting further away from the origin. This is an increase in x, this is an increase in y, so we'd be getting further from the origin. If the coefficient C1 were negative, we'd be down here, getting further away in the negative direction. So we've added the arrows to our eigenlines, and then step 3 is to add other trajectories based on the arrows. So based on the arrows, we just kind of fill in now with some other trajectories. That's maybe the least precise part of this process. I just kind of draw some curves that kind of fit the same arrows. And these are the solution trajectories for our phase portrait. I now have a rough sketch of the phase portrait. Maybe not as good as a computer would do, but it does tell me what's going on. I just want to say something about reading the phase portrait. How are we going to make sense of the phase portrait? Let's say let's say that, I hope that that's showing up. Let's say that x of 0 is 1 comma minus 3. 1 comma minus 3 puts us like down here. If that's my initial condition, my trajectory is going to go like this. That gives me an idea of what the solution would look like if I started at 1 comma minus 3. How do I translate that? Well, up is positive, down is negative for y. Right is positive, left is negative for x. So if I start here, what is x doing? I'm moving to the left everywhere throughout this. So x is just straight decreasing. Let's sketch x and y as functions of t. X starts at 1, y starts at -3. Those are the initial conditions. And x is just a decreasing function because this phase line, this trajectory is moving to the left, which is decreasing in x, right? Now, in y, this phase line actually goes up a little bit before it goes down. So y increases just a little bit and then starts to decrease, and y is going to look something like this. They both end up going towards negative infinity. They both go down towards negative infinity in the limit as time increases. But y has a little bit of an increase before it decreases because it goes up and then down, whereas x just goes left, 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 which is down, 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 down. So that is how to translate that one trajectory on the phase portrait into these two solutions. The point of the phase portrait is that I see all of the possible trajectories at once. So I know that if I start here, for example, I'll end up at positive infinity for x, positive infinity for y. If I start here, same story. But if I start here, I'll end up at negative infinity for x and for y. So I can see general behaviors of solutions based on different regions of the phase portrait. That's something we can't see from just individual solutions. We have to see it in the phase portrait to get it all at once. That's an example of the steps that we want to follow to create one of these phase portraits.